This is an example problem associated with lecture 3. So we're going to do this the same way we did before, in that we'll do it in 2 lectures, just to make YouTube happy. So essentially what we're going to do this time is just talk about it. And then in the next lecture in the next video we'll go solve the problem. Okay, so this is another problem, has a RAM in it, and that means anytime I have RAM in it, I know there's going to be a counter in it. The counter output is going to provide an address for the RAM. We do it every time. So this RAM happens to be a 32 by 8 RAM, so the counter width that I'm going to use to address this RAM is going to be 5 bits. So this circuit is another circuit that's counting something. Never mind what it's counting right now, but the implication there is that I need a counter to count something. So we saw that in the last example, where it was essentially an event counter, where I was essentially incrementing the counter every time it detected that event. And so this is a similar problem, in that I'm counting events, but the event's a little bit different than last time. So the event is when the one piece of data in memory is greater than the previous piece of data in memory. So the implication here is the data is at contiguous addresses. So essentially, if the data at memory address 6 is greater than the data at memory address 5, I'm going to essentially increment the counter. And when all that's done, I'm going to display the result. So all this happens, of course, when it gets a go signal, and the go signal turns on, and I start counting. What I'm going to do here is step through all 32 locations of the RAM. And once again, I'm going to use the counter for that. Essentially, it's an up counter, just incrementing through every clock cycle. So the issue on this problem is the output counter is the width of the thing. And so, the previous problem, we actually had to add an extra bit to it. But if you think about this problem, the highest the counter could be is based on the fact that this condition right here is taken into effect. Essentially, we're going to ignore address 0. We're actually going to start at address 1. Kind of, sort of. That's not what we're going to do. Essentially, I need to design the circuit such that I'm looking at 2 addresses. So the notion in the circuit is that I need an extra register. I just can't look at the output of the RAM. I have to actually store the previous output somewhere, and I'm going to store the previous output in a register, of course. Okay, so in the end, this circuit's going to have 3 registers. 2 of them are counters, and 1 is just an intermediate storage register. Okay, so the issue, what I want to do here is make sure I essentially, this is this condition right here, essentially I have to make sure I fill that register before I start counting, which means I'm not going to start the count at 0, so the maximum the count can be now is 15, which is going to happen if the data in RAM is in ascending order, which is possible. So if the data in RAM is in ascending order, the maximum the count can be is 15, and that's going to allow me to use a 4-bit counter on the output. And so once again, we got a RAM, which is 32 by 8. We have a counter that's driving that RAM, and it's going to be a 5-bit counter. We have an extra register. This is this essentially holds previous values from RAM, and certainly it's doing some type of comparison in here, so we need a comparator. And lastly, let's see, another counter on the output. This is going to be a 4-bit counter, and this is going to count the number of occurrences. And lastly, we need a state machine to control this thing. And I think with that, I think we're ready to solve this problem. And I can't think of anything else on this. Let's just go to the next lecture and take care of it.